Okay. Hello, everybody. My name is Aniket Kate, and today I'm going to talk to you about how to build the giant MPC systems using lightweight cryptography. Uh, so let's dive into that. So I'm going to use a more generic term, although we can relate many of the things that I'll be talking about with multi-party computation. But I'm going to use a more generic term to define where the techniques that I'm going to discuss will be applicable. And that generic term is secure distributed computing, or SDC. So it involves basically building any distributed systems, but you want to add confidentiality and secrecy on top of that. And the applications for that are numerous. You must have seen several of these examples. What are you building? For example, verifiable secret sharing, distributed key generation, building beacons, common coin, multi-party computation in general, as we looked at in some of earlier talks, and as well as several other things, including blockchain itself, can be looked into in this particular fashion. So when we consider this scene, let me first talk about the setting. So I'm considering blockchain as my primary example, and that's the reason I'm going to assume that we have no assumption on the networking in general. We work in the worst possible scenario, that is asynchronous message delivery. And we are going to assume that we have secure channel based on SSL and TLS so that the participants there can talk to each other efficiently in a secure and authenticated fashion, which will continue to remain also in the post-quantum world. And then again meet the setting, the decentralization level that I'm considering, that I have up to thousands of nodes, and I'm thinking of optimal fault tolerance of 33% malicious parties, which is optimal in this case. So the key differentiator is there may exist systems which can go for higher value of n, but if they reduce the fault tolerance lower, then they become not comparable. If that's your setting, I'll be happy to discuss with you because the techniques can be still applicable, or maybe it's more interesting things can be possible if your number of nodes are higher, but the fault tolerance can be lower. So moving on, in such setting, when we go for the security notion for all these MPC or SDC protocols, here is how things stand. One is that you work on this, what is known as unconditional security. So that means you build protocol based on just coding theory ideas. You will have perfect or statistical security in this case. But the drawback is that the communication overhead that there is significant. It's like n raised to 5. And if you say 1,000 nodes and you're such a big number, then indeed this can be quite significant number. And if you go for, in particular, multi-party computation in this setting, you can see that huge number of n raised to 14. That's the state-of-the-art construction that's present over there. So certainly quite theoretical in general. On the other hand, many things that are happening in the blockchain space or otherwise are more in the computational setting, where the idea is that you make cryptographic assumptions such as discrete logarithm problem, pairing, FHE, and you work on setups like power of tau setup, you assume you have distributed key generation done, or PKI done, and you try to build better protocols. And indeed, the communication overhead or complexity there is much lower, maybe quadratic or cubic in some scenarios, or maybe linear by using batching techniques. However, the drawback there, which is not often considered, is that they come with the cryptographic operations, which easily require 1 millisecond per each of them. So by themselves, they look small, but once we add up with them and make them where those costs are, let's say, linear in the number of parties, these things add up. I mean, just to give a extreme example, if we assume FHE and if you want verifiability for decryption, then we are easily talking about several seconds, even with the making some concession, or maybe just we are not able to even do this operation in some other consideration. So indeed, there are bounds when it comes to the computational security. So overall, based on that slide, what we typically see in practice is that unconditional MPC and SDC is just complete theory, and research efforts are generally to make sure that we reduce the communication complexity, typically to the cubic or quadratic, and use batching technique to further reduce that if we can. We also try to reduce the number of rounds in such scenarios so that maybe it's just non-interactive as happened with FHE, or with fewer number of rounds as we can, and reduce the numbers if there. But typically, whatever experiments which are in this case are restricted to 50 nodes or some domain like that. And it raises interesting question, is it really practically useful? At least for the setting that I build up, it's not. right? So the question that we ask is that why can't we just do why can't we just buy better machines and deal with this computation cost that we are questioning here in when we talk about computational security? And I want to give 3 reasons. Let me start with the easier reason. A is that better machines which has hardware acceleration whatsoever can be costly. So if you want to scale with them, it's going to increase the cost on your infrastructure. It's also a limit because even there is a limit to how much you can do better with respect to computation. We can only parallelize up to a particular level, so that's also a challenge. But the most important thing is that most of the better machines and most of the current blockchain that are coming with much better communication infrastructure. We have blockchains now which we have sub-second level of latency and really high throughput in 100 kTps or more than that, just to give you an example. And we are ignoring them when we are just focusing on all these computationally heavy operations and heavy tasks as we do with the FHA and other approaches, just to give you an example. And then we are, indeed, I want to give a more concrete example to see what we observe when we start really build these solutions and what we observe. And the key message there is computation overhead cannot be ignored. Going into more detail, so this is my own work that I done with collaborators. What we observe that when we build these MPC solutions, and we want properties where we have computational guarantees, and we went for a protocol which is not does not have guaranteed output delivery, but still more efficient and make it work. And I want to just show one example from there. So I had 2 ways to solve a problem of anonymous broadcast. One had fewer number of rounds, has lower communication complexity, but has more computation complexity. And that's my first line in the table I'm showing. And the second one has many more number of rounds and much more communication, but cheaper in terms of the computation. And in all our experiment, the second one win. So it shows that when we work into real world, rather than just focusing on reducing the communication complexity around, we should also consider the computation overhead and build protocol which can actually use this both communication as well as computation in a trade-off fashion to do a better job. And that's something which I observed from my own experiment. So indeed, the question is that how to deal with this computation versus communication trade-off. Can we have some intermediate solution which try to do the best in the both world for MPC in general? And that's where now I want to introduce this, I guess, one of the newer concepts which we call as lightweight cryptography. So what I'm going to do is that I want to have all my multi-party computation kind of guarantees, but I only want to use hash functions, where I'm going to use them as a random oracle or quantum random oracle and nothing more. In some application, maybe we can consider signatures and PKI, but let's say for this talk, you can also ignore it. And the key thing I want to look at them is for this purpose that I'm showing in chart, right? So if you look at all these cryptographic tasks, they're easily 1,000 times more expensive than hash computations or symmetric key operations in general. And that difference can help me a lot to overcome the barrier and reduce the computation cost and use that communication to do a better job. And my rest of the discussion in this talk will be to give interesting example that we observe in this space and that we're building to show real performance where this is going to make a difference. And again, and the cherry on top, because we are only dealing with hash functions, there exist settings and cryptographic model where we could be using this for the post-quantum security, and that certainly is something that interests me a lot. So let me start with the simplest, one of the core primitive in this space, which is verifiable secret sharing. And we know how to do verifiable secret sharing computation setting with the quadratic communication complexity. But it uses operations such as discrete logarithm, polynomial commitment, verifiable multi-receiver encryption, primitives like that, which can be expensive. And the question that we ask that, okay, I want to just use hash functions and secure channel, and can I build AVSS? And answer is obviously yes. We did that in some of our earlier work. And recently, actually, this got further improved so that the cost there reduced from cubic to quadratic. So some improvement has indeed happened in that particular space. She's demonstrating that indeed we can reduce the computation cost and try to get the best of the both world in this environment. And very recently, we also start to look at now asynchronous MPC, the MPC version of this problem, to see what can we do. Here, when we are building MPC, I'll be building arithmetic circuit. That means everything is represented as addition and multiplications. And as I already mentioned, the state of the art here is an extremely expensive protocol which has this n raised to 14 terms. You can see over there. And the question is that can we build MPC just with this lightweight cryptography primitive or hash functions? And we observe that indeed this is possible if we want only fairness guarantee. That means if the honest parties get output or adversary get output, honest party will also get output. Such kind of guarantee, we can manage that with the cubic complexity overhead itself. So C term over there talks about how many gates you have in circuit. So you can just ignore that N and C term, just focus on the second term, which is a cubic. And even if you want a better guarantee, we know how to achieve that with quadratic complexity, n raised to 4 complexity. And the important thing is the computation costs are just hash function computations, and they will continue to remain efficient even when n goes to up to 1,000 in this particular scenario. And we will have performance results soon. But indeed, unless I show you performance, you won't be happy, right? So let me at least talk about something that we already implemented, some of the examples that we already built, and we observe that indeed we can get performance. So this is what we achieved last year, where we take one specialized MPC, which is generating random beacon, and we try to build that protocol just in this lightweight cryptography domain and see what we observe, right? So I assume everybody here knows what are random beacons, but just to give idea, so random beacons is the source where you can generate secure randomness that you can use for all applications. And there are many applications in blockchain space that all of you might already know, aware of. There exists centralized, more like Web2 solutions, but single point of failure is an issue for that. And that's the reason we have what is known as distributed random beacon protocols, where you have not trust on a single party, but you work on a distributed setting. And as long as some majority of them are continue to function great, you will be able to create beacons, as I'm showing on the screen over here, that R1, R2, R3, these are the beacon values that are present over here. And they offer, you want to make sure that we have a guarantee such as the consistency of output or agreement that we should be able to generate beacons. And we want to make sure that they are not, they cannot be biased, that they remain unpredictable. And all these guarantees can be achieved. And now, what we observe that for sure there are nice solutions that exist in this space. For example, Definity VRF, Supra has VRF service, DRAN you might have heard about or use as well. They all can provide these threshold unique signatures, and they have this DKG setup, distributed key generation setup, and they can provide you the answers. But there's no post-quantum security, and also the reconfiguration itself can become a challenging aspect when we consider these protocols. And then the interesting question there is that what can we do towards overcoming this case? And I won't be able to go through the protocols. I encourage you to go to the paper or the code over here. And we build this protocol. We compare them with the state-of-the-art protocol that are available that uses expensive cryptography, like discrete. For me, expensive means discrete logarithm operations and exponentiation and stuff like that. And what we observe is that indeed we can get much better result even in that setting. For example, just to give, so this HashRAND, which only use hash functions, was able to provide substantial margin over this PERT, which is a state-of-the-art known random beacon protocol when we work in non-synchronous setting. And there's a significant difference that we observe even when the number of nodes continue to grow. Another thing that we observe is that we can make this protocol work for really large values of n. I mean, this is done more in the simplified setting, but protocol can continue to work for really large values of n as well. And then we observe that we can, it's also better than even when we use this DKG setup and pre-quantum security, we can continue to achieve that where our protocol will have post-quantum security. And finally, performance also can be improved because the hash computation, if you put that on hardware, then performance can be improved even 10 more times, making it even much more efficient. But not just one. I have one more example for you. So this is something that we recently worked on, where we take the example of what you know as dynamic proactive secret sharing, and then we ask question, I want to do this operation, and I want to use again hashes. What can you achieve? So what is dynamic proactive secret sharing? So the another term, more Web3 term can be that how can blockchain keep secret? So let's say they are secret for users or client that a committee is mentioning. So here I'm showing an example with the 4 committee members who are maintaining this information. But we want to make sure that there is a reorganization possible, so that when we go from this committee to some other node of committee, let's say I kept the number 4 same, but other parties change, right? And you can keep on working in such an environment where you continue to improve or change the organization. Here for simplicity, I kept the number of nodes to be same, let's say 4 here. But you can expect that the parties themselves can change. Some parties get added, there were more parties earlier, now there are less parties. All these configurations are present, and basically that's the most dynamic scenario you can assume, so that the secret are continued to maintain by blockchains or this committee of nodes. And the question that we ask, that how can we achieve such a setting and such a particular MPC instance? And again, the state of the art here are these 2 efforts. Cobra, which uses again verifiable encryptions, and so is the long-live honey badger, and they all use again cryptographically more expensive operation than hash functions. And then we question that, okay, I want to replace them, just use hash functions as my only operation and secure channel, and can I do better? And what we observe that, yeah, we add more onto the communication complexity, but still when we implement this protocol, we are able to overcome the state of the art with latency which is much lower in the same setting. And we are able to perform much better than that. But more importantly, even when the number of shares or number of secrets that such a committee has to maintain grows, in our case, let's say they want to maintain 10,000 secrets, even for n is equal to 88, we can go to around 82 seconds. And this is just like the first implementation we achieved. We can continue to improve on that, and these numbers can drop quite significantly. And as always, the cherry on top, we can achieve security like post-quantum security. So yeah, those are the 2 examples I worked on. I hope that I have numbers to share with you when we build a full-scale MPC on that, but hopefully in March we'll be ready with that. But my key message I want to give is that we are building solutions for confidential computation with FHE and other mechanisms. Certainly I can't compare with TE in terms of performance, but where we only consider this one axis of no communication, and we continue to perform much better, continue to improve our hardware or add more hardware, and try to do them in a aspects which is less on communication, but heavy on computation. But this talk, I want to give an example that actually most of our environment come with really good communication methodologies as well, and we should really utilize them while solving the problem. And by no means MPC is always your best solution. There exactly exist scenarios where we should use FHE or technology like that to solve the problem. But there are indeed applications where MPC will continue to do much better job, and we should consider in those scenarios applications such as lightweight cryptography with MPC. And indeed, we can get much better trade-off there and post-quantum security, so we should consider these applications in general. And finally, I want to end my talk by giving this one message that indeed the amount of efforts and amount of money that came to zero-knowledge proofs and FHE are leading into significant improvement in this space with respect to better protocol, better implementation. And MPC also need and want similar love, and it can actually make MPC-based confidential compute much better and much accessible and much usable and soon. And indeed, this not only in this room but in general, blockchain community should consider MPC and work towards it. Thank you.